Hi, I'm Margaret Smith. I'm a professor of plant breeding at Cornell University, and we're standing in my corn breeding nursery in Aurora, New York. We're going to talk a little bit today about the story of hybrid corn. That's a story that goes back to two people, George Harrison Shull and Edwin Murray East. They were scientists in the early 1900s who wanted to understand more about the genetics of important traits in plants. They chose to study corn because corn is particularly useful in two ways. First, it was an important agricultural crop, so finding better varieties with better genetics was important. And second, it's an especially convenient plant for genetic studies. It's convenient because the male flower or the tassel is separated from the female flower or the ear. So I want to give you a quick review of how corn pollinates. In the tassel is where the male flowers are. They shed lots of pollen when the tassel is bumped by the wind. You can see that big drift come out. That's the male gametes of the corn plant. In the ear is where you find the female. This starts off as a little shoot behind the leaf sheath, and then eventually the silks grow out. And when you peel that shoot, this is what it looks like. There's a silk going to, at the base, an ovule or an egg cell. And each of those egg cells is what will grow into a kernel on the fertilized ear of corn. So to pollinate, the wind blows the pollen out of the tassel. Some pollen has to land on each one of the silks and then grow all the way down those silks to fertilize the ovule or egg at the base. That fertilized egg is what grows into a kernel of corn. In their experiments on the genetics of plants, both George Shull and Edwin East did two different things. They self-pollinated or produced homozygous inbred lines, and then they crossed those inbreds. Remember, they were trying to understand traits, but they had to be able to control pollination. So to create a homozygous line to inbreed, what you do is you take the pollen from a plant and you use it to fertilize itself. So they would cover the ear shoot before it put out silks to make sure it wasn't crossed at random, then collect pollen from the tassel they wanted to use, lots of pollen, and then very carefully and very quickly pour that pollen on the silks of the same plant and cover it up. Then they knew that plant had been self-pollinated. Repeatedly self-pollinating is what made a plant eventually homozygous or inbred. They then took those inbreds, different inbreds, and made crosses between them. So in that case, they would take pollen from a different plant, again, shake it off, and use it to pollinate a plant that you wanted to make a cross with. There it is. And cover it up. These things had to be done quickly in the field so that the silks would not get pollinated at random with any other source of pollen that was floating around out there. So remember, the first part that I talked about was that both Shull and East did studies involving multiple generations of self-pollination to create inbreds. They started with big, vigorous plants that had big, productive ears. They self-pollinated for one generation, and then another, and another, and another. And by the time they got to 4 generations of self-pollination, they had plants that were quite inbred or homozygous. You can see they were much less vigorous, and they had much smaller ears. You might wonder what good that was to anybody. That's a good question, and that's the next part of the story. So it was no surprise in 1908 when Shull published the fact that inbred lines, pure homozygous lines, were less vigorous and had poorer yield. The next part of the study, however, was to cross inbred lines together. So he took 2 different, very weak, low-yielding inbred lines and crossed them together to make a hybrid. And that hybrid could look as good as this. That is what hybrid vigor is. And that was the part of the story that led to improvements in corn for growers in the United States. This seed that's the product of a cross between those two is an F1 or a single cross hybrid. If you get the right one, it has higher vigor, taller plants, bigger leaves, faster growth, and more seed on the ear, all things which were potentially very useful to farmers. This plant then would be an F1 single cross hybrid, and the vigor it shows is called hybrid vigor or heterosis. We understand heterosis as the combination of desirable genes that you get from crossing 2 different parents with each other. There are 32,000 genes in corn, and it's hard to have all the desirable ones in just one homozygous parent. By crossing two together, you have a better chance to get more desirable genes in that F1 single cross, making it higher vigor and higher yield. That, we think, is the basis for heterosis or hybrid vigor. So Schall and East both made crosses between many different inbreds. Not all of them produced good hybrids. Some of them were excellent, others not so much. And it depended on how well the genes in the two inbred parents complemented each other. Some hybrids got fewer desirable genes, and others got a lot. The key was to pick the best hybrids from among all those crosses and then go back to their inbred parents to make that hybrid again for seed to sell to farmers. Those hybrids were made by planting the two inbred parents in a field where there was no other corn pollen, and then removing the tassels from one of them so that all the seed harvested from it would be from crosses with the other inbred parent. That's how F1 hybrid seed was made, sold to farmers, and that's what farmers grow to get their corn crop. Building on the work of many scientists before them, both Schall and East made a clear connection between the negative effects of inbreeding and the positive effects of outbreeding, or in this case, hybrids. The work was pivotal because it shifted the focus in plant breeding from that of seeking the best inbred parents to rather seeking the best hybrids in order to accomplish higher yields and more productivity in agricultural crops.